Hello, in this video we're going to talk about cofactor expansion along a row and a column, and then we're going to talk about some equivalence conditions for A to be invertible. So here is the first thing we're going to do. The first thing is what we call the cofactor expansion. So what is cofactor expansion along a row or a column? It allows us to find determinant of a matrix in a different way. Let me start with an example to see how cofactor expansion works, and then we will do the theorem in general. So here's an example. Let's say you want to evaluate the determinant of a 3 by 3 matrix: A11, A12, A13, A21, A22, A23, A31, A32, A33. And I'm going to do this cofactor expansion along the first row. So here is how it works. You start from one of the entries, let's say A11, and you'll have to do that for all of the entries. So you'll start from A11, which is the first entry of the first row. You have a plus minus sign in front of it. The sign is -1 to the power of 1 plus 1, A11, and then determinant of. You remove that row and that column, and you get a 2 by 2 determinant: A22, A23, A32, A33. Then you move on to the next entry, plus -1 to the power of the number of row, which is 1, plus the number of column, which is 2. A12, determinant of. Now we are going to remove this column and this row, the row and column corresponding to that entry, and we are left with A21, A23, A31, and A33. So in other words, we go from a 2 by 2 determinant, 3 by 3 determinant to a 2 by 2 determinant. Now we're going to take that, eliminate this row, eliminate this column, and eliminate that row. -1 to the power of first row, third column, A13, and then we're left with a 2 by 2 determinant: A21, A22, A31, A32. After evaluating the determinants of the 2 by 2 determinants, we'll be able to evaluate this 3 by 3 determinant. Now, why is this true and why does this work? So here is how we're going to prove this one. I'm going to prove it for the first row, expansion along the first row, and the others are going to be quite similar. So let's just say you want to evaluate the determinant of A11, A12, all the way to A1n, AN1, AN2, all the way to ANN. We are going to use the multilinearity with respect to the first row. So this is determinant of the first row is A11 E1 plus A12 E2 plus A1n En. And I'm going to keep the rest. The rest is A21, A22, etc. A2n all the way to AN1, AN2, ANN. Okay, so let's see how we can actually use linearity. So when you use linearity, the first entry would become A11 and then E1, so it becomes A11 determinant of E1, and then the second row A21 all the way to A2n, all the way to the nth row, AN1 all the way to ANN. And then the next one becomes A12, and then determinant of E2, A21 all the way to A2n, ANN all the way to AN1 all the way to ANN, plus, and the last one becomes A1n, determinant of En, and then the second row A21 all the way to A2n, and the last row AN1 all the way to ANN. So this is what we get. Now, in order to solve the problem, to prove the theorem, we need to show this is in fact determinant of the matrix when you remove the first row and the first column. If we go back and look at cofactor expansion, it tells us it's negative 1 to the power of I plus j times aij times determinant of a sub ij, which is the matrix obtained by removing the ith row and the jth column. So we need to show this guy is negative 1 to the power of 1 plus n, 1 plus 1, which is the first row, first column, and then determinant of when you remove the first row and the first column. So let's look at that. So that's determinant of E1 is 1, 0, 0, 0, 0, A21, A22, A2n, all the way to AN1, AN2, ANN. Now, we can use row operations and get rid of all of these. We multiply the first row by A21 and subtract it from the second row. So I can make all of these 0. So this becomes 1, 0, 0, 0, 0, and then 0 here as well. And this is in fact A11. This is the matrix obtained by removing the first row and the first column. Now, when you apply row operations to this matrix, to the entire matrix, it is exactly like applying the row operations to this matrix. So when you apply this, you get to determinant of A11. Because the row operations that reduce this one to the identity matrix are exactly the row operations that apply to A11. And if A11, the rows of A11 are linearly dependent, then we end up with an echelon form that is 0 at the bottom. And that would again mean the same thing. That would mean that the determinant of this one is A11. Now, what if you look at the next determinant? The next determinant is going to be 0, 1, 0, 0, 0. And then A21, A22, A23, etc. A2n. We can do the exact same thing to make the second column 0. So we can do 1, 0, 0, 0, 0. Then make the second column 0. And if you do that and swap the first column and the second column, A23 here all the way to AN3. If you do that, you get negative determinant of 1, 0, 0, 0, 0, 0, 0, 0, and this is A sub, we remove the first row and the third and the second column. And this is negative determinant of 8, 1, 2. And it's going to be very similar for the other ones as well. So when you have in the first row determinant of EI and then A21, A2n, etc., that becomes negative 1 to the power of, you need to move EI to the front, so you will get negative 1 to the power of exactly 1 plus I. That's how many swaps you need. So you need basically I minus 1, which is the same thing as I plus 1. Determinant of 1 and then 0 here after you do row operation, and then A1I, which is negative 1 to the power of 1 plus I, determinant of A1I. Okay, so this proves the cofactor expansion along the first row. And if you want to do a cofactor expansion along a different row, you'll just do swapping, row interchange, and then you apply cofactor expansion along the first row, and that would complete the proof for cofactor expansion. How about cofactor expansion along a column? So that would prove the cofactor expansion along a row. How about cofactor expansion along a column? So all you need to do is to use the fact that determinant of A transpose is the same as determinant of A. So a cofactor expansion along rows of A transpose is going to be the same as cofactor expansion along columns of A. And that also is not very difficult to see. Okay, so we're going to continue with one example. A square matrix A is called invertible or non-singular if there is a matrix B for which AB and BA are both identity. A matrix is that is not invertible is called singular. Let me talk about that a little bit, and then we'll get to do an example. If you recall, when you start from a matrix A, we can do row operations to get to either identity matrix or a matrix that has zeros at the bottom. So let's just start from a matrix A and assume that we get to the identity. So after you do these row operations, the first row operation gives you a matrix, elementary matrix on the left times, so let me put it right here. So you start from A, you do an elementary row operation, you get E1A, then E2 E1A, etc. all the way to EM E1A. At some point you end up with identity. Now if you look at EM through E1, that matrix times A is in fact identity matrix. This is assuming that you end up with the identity matrix after you do these row operations. Now, each of these elementary row operations, we know they are invertible. So let's multiply by their inverses. So EM inverse, EM all the way to E1 times A equals identity. And if we do that, equals identity equals EM inverse, because I multiplied by EM inverse from the left. So if you do that, you'll end up getting EM minus 1 through E1, because EM minus 1, EM inverse EM cancels. So we get EM minus 1, E1A equals EM inverse. Multiply by EM minus 1 inverse, we get EM minus 2, E1A equals EM minus 1 inverse EM inverse. So if you continue with this, you end up getting A equals E1 inverse all the way to EM inverse. Now multiply by EM from the right. You get A E1 EM equals E1 inverse all the way to EM minus 1 inverse. Continue with this, you end up getting A times EM all the way to E1 is identity. So as you see, this guy is in fact the inverse of A. So EM all the way to E1 is in fact inverse of A. Because the multiplication for matrices is not commutative, so I can't just swap the order of multiplication. Now the question is, how do we find this inverse? And here's how we find the inverse. In order to find the inverse of a matrix A, we start with an augmented matrix AI, and we apply these row operations. So the first row operation is going to give us this matrix. I'm going to apply that to the entire matrix. The first part of this matrix gives us eventually the identity matrix, and the second part gives us the inverse. So then you do E2 E1A and then E2 E1. After you continue with this, you end up getting EM E1A and then EM multiplied by E1. So that is exactly identity. As soon as you get to identity, the other portion gives you the inverse. So this would be inverse of A based on the discussion that we just had. So now we are ready to do an example. We want to find the inverse of this matrix. So what we do is we take the matrix and we put it in an augmented matrix. We do row operations. The second portion of the matrix give us the inverse as long as we get to the identity matrix on the left. So we are going to apply row 3 minus 2 row 1. So 1 1 2 1 0 0 0 1 3 0 1 0. So this would be 0. We are multiplying the first row by -2, adding to the last row. -4, -2, 0, and 1. Okay, So that's the first step. Now we are going to add row 2 to row 3, and also row 1 minus row 2. So this gives us, so row 2 remains intact, row 1 minus row 2, so this would be 1 0 minus 1 1 negative 1 0, and then we are adding the second row to the third row, so 0 0 negative 1 negative 2 1 and 1. Now let's make these two 0, so this would be row 1 minus row 3, and then row 2 plus 3 row 3. Okay, so if we do that, we're going to end up with 1 0. So we are doing row 1 minus row 3, so that would be 0. 1 minus minus 2, that's 3. Minus 2 here, and then minus 1. 0 1. So we are adding 3 times the third row to the second row. That would be 0. Minus 6 4 3. 0 0. And then we could also negate the last row. Last row becomes 1 2 negative 1 negative 1. So the inverse of the given matrix is 3 negative 2 negative 1 negative 6 4 3 2 negative 1 negative 1. That's the inverse of the original matrix that they gave us. 1 1 2 0 1 3, I believe, and then 2 1 0. And we could check that in fact this is valid by multiplying them. So this one times this gives us 3 minus 6 and then plus 4, which is 1. This first row times this one gives us negative 2 plus 4 minus 2, which is 0. The first row times the third column becomes negative 1 plus 3 minus 2, that's also 0. Second row gives us, second row times the first column gives us negative 6 plus 6, which is 0. Second row times the second column gives us 0 plus 4 minus 3, which is 1, which is what we want. Second row times the last column, dot product becomes 0 3 negative 3, which is 0, which is what we want. Last row dotted with the first column, 6 minus 6 plus 0, which is 0. Last row times multiplied dot product with the second column is negative 4 plus 4 plus 0, which is 0. And then finally last row dotted with the last column is negative 2 plus 3, which is 1. And that gives us the final answer. Okay, let's now look at this important theorem. This theorem tells us when a matrix is invertible. So it tells us this: the following are equivalent. A is invertible, determinant of A is non-zero, rows of A are linearly independent, columns of A are linearly independent. These four things are equivalent. So what does that mean? It means if one of them is true, then the other ones are also true. So the best way of doing problems like this when you're trying to prove equivalences is to show like there's a cycle here. So A implies B, implies C, implies D, and then D implies A. So that's really what you are looking for. Now, it may not be the easiest one. The A implies B implies C implies D implies A. That may not be the best cycle, but some cycle would be really the best to do. But it's not always also possible. Sometimes you may have to choose, show that two of them are equivalent like more directly, but this is usually the fastest way of doing that. So let's just start with A implies B. So if A is invertible, we want to show that determinant of A is non-zero. So since A is invertible, A times B is identity. Now let's take the determinant of both sides. Determinant of AB, so assume A is invertible. So there is B such that A times B is identity. That's like the definition of invertible. So this is equal to the determinant of identity, which is 1. So that tells us determinant of A times determinant of B is 1. But if product of two things is 1, neither of them are 0. So determinant of A cannot be 0. Okay, so let's prove B implies C. Determinant is non-zero. We want to show that rows are linearly independent. Okay, so rows are linearly independent. We had seen something about rows being linearly dependent. So suppose determinant of A is not 0. On the contrary, assume rows of A are linearly dependent. We had seen before that determinant would have to be 0, which is a contradiction. Okay, so that really immediately follows from what we had seen before. Okay, C implies D. Rows are linearly independent and columns are linearly independent. So if rows are linearly independent, we want to show that the columns are also linearly independent. Okay, so let's try it this way. So if rows are linearly independent, what does that mean? It means there are n pivot entries. So suppose A is n by n. We have seen that we have assumed that A is a square matrix. That's crucial because we can't really talk about determinant invertibility for non-square matrices. Suppose A is n by n, and its rows are linearly independent. So I want to show that the columns are also linearly independent. So by a theorem, if the rows are linearly independent, there would have to be a pivot entry in every row. There is a pivot entry in every row of the reduced echelon form. But A is a square matrix. There are n pivot entries. So since A is n by n, every column is also a pivot column. Every column is a pivot column, which means columns of A are linearly independent. Okay, so finally we want to show that D implies A. So why is it that D implies A? If columns of A are linearly independent, we want to show that A is in fact invertible. So how do we show that? So one way would be to basically similar argument shows that their rows are also linearly independent. But you could also basically kind of directly argue, since columns are linearly independent, there would have to be n pivot columns. There would have to be n pivot entries. So since A is n by n and n columns of A are linearly independent, the reduced echelon form, there's only one possibility for that. Is the identity matrix. But what does that mean? It means some elementary matrices, when they are multiplied by A, we get identity. For some elementary matrices, E1 through En. Now, we just saw earlier, so we saw earlier that A times EM through E1 is also identity. And that means, because I need to have both of them, and that means A is invertible. And that brings me to the end of this video. So next time, we're going to talk about Cramer's rule and how to find the inverse of a matrix with a different method. I will see you in the next video.